Okay, I guess we can get started. Welcome to today's Science and Engineering Council meeting. You want to put here's our sponsors slide, but then you can go back to the. We're happy to have you here. We have our meetings every month with technical talks from various people in industry and UCSB professors. So let's see, as far as board members, we have Joseph here today, and we have Bill Theringer, and online we have Mary Howe Grant and Stephen Skopatz. Anybody else? That's it as far as board members.
Yes.
And myself, I'm Yvonne DeGraw. I'm the programs chair. And just wanted to give you a heads up about some of our upcoming meetings. On August 14th, we'll have Dr. Susanna Scott, a chemical engineering and chemistry and biochemistry professor at UCSB. She'll be speaking on a new way to recycle plastic, the circular carbon approach. Our talk for September is still to be announced, but we're in the process of firming that up. On October 9th, we'll have Dr. Allison Santoro from UCSB speaking about engineering biodegradable plastics for tomorrow's ocean. So a couple of interesting plastic talks coming up, and hope you'll be able to attend those. Today, we're happy to have Dr. Cassandra Phillips speaking to us. She is the Senior Product Manager for Bruker Nano. Dr. Phillips is the Product Manager for Nanoscale IR spectroscopy at Bruker Nano. She works on developing the next generation of nano IR products and getting the word out about this technology. Cassandra began working at Bruker in Santa Barbara as an application scientist in 2019 after completing her PhD at the University of Toronto in Canada, where she studied the infrared photophysics of boron nitride nanotubes. We're happy to have her speaking to us today. Here you go. So, great. We'll be sharing her screen. Do we want to zoom in? Yeah. Sharing. There we go. Go. Okay.
Behind the chart.
Okay.
Great. Thank you for the introduction, Yvonne, and thank you for the opportunity to speak here today. I think this is a really exciting group that you have together. I think, ultimately, if you look at Santa Barbara, it really punches above its weight in terms of technical innovations. And so to have a community of people here learning about what's happening both at UCSB, but also beyond this, I think is extremely valuable. So as Yvonne said, I'm the Senior Product Manager for Nanoscale Infrared Spectroscopy at Bruker Nano. If you don't know Bruker Nano, it's actually just up the road from here on Robin Hill Road, behind the hotel right there. And it's a very large company. It's about 7,000 people worldwide. But within Santa Barbara, there's about 200 people who are all dedicated to atomic force microscopy technology, both developing the next generation of technology, but also manufacturing and delivering it to customers in academia and beyond. So today, my talk is broken into 4 different sections. The first thing is going to be a motivation, where we're going to talk about why we care about nanoscale infrared at all. Why am I here? Why am I employed by Bruker? Then we're going to look at the development history of this really exciting technology, and in particular, what the strong Santa Barbara connection behind this development is. And then we're going to break into 2 different application sections where we're going to look at how AFM-IR is being used to ask big questions in the cosmos, and how we can use it to be healthier as a civilization. So first, I want to start with the number 1 question, which is, why spectroscopy, why infrared, and why nanoscale at all. And to start, I'm very happy I've eaten already because I have a very nice picture of a stew. And so when you're looking at this stew, I want you to close your eyes and think about what you're smelling as you're cooking this nice hearty meal. You'll smell the spices that you put in. Maybe you have some aromatics, some thyme. Maybe there's tomato sauce. If you have some meat in there, you might smell the kind of releasing of the fat and the aerosolization of all of that, right? It's a pretty mouth-watering experience to just close your eyes and smell as you're cooking. It's really quite fantastic. Next, I want you to open your eyes, plug your nose, and take a sip. When you do that, the world gets a lot less complex. You'll taste maybe some salt, you'll taste maybe some fat or some umami texture, but ultimately you don't get the same repetition and differentiation of all the ingredients that went into the soup. And so what I'm here to tell you today is spectroscopy is the sense of smell of the electromagnetic spectrum. So it really provides this richer view of what is going on in a material, what that material is all about, and helps us for both scientific discoveries, but also engineering applications. So that's why spectroscopy, but now why infrared? So here I have the electromagnetic spectrum laid out, and spectroscopy is really a valuable method to probe molecular information in materials. So, we know we have this very small visible range, and then as you go to longer and longer wavelengths, we start to look at the infrared, the microwave, radio waves, which are often used in communication. And as we go to higher or shorter wavelengths, higher energy, you're looking at UV, you're looking at X-rays, and in that region. But what's really useful about this is really comes back to the fundamental nature of molecules and materials, which is that things are energetically quantized. So you might have heard this idea before of things being quantized, but practically what this looks like is we have this kind of ladder of energy states. So here we're looking at the scale, and as you go up in energy, you have these different discrete levels of allowed energy within a material. And so these are broken into different categories. If you look at these kind of medium-sized graphs, these are vibrational modes, which are accessible by the mid-infrared, which we're going to be talking a lot about today. Then you have these smaller modes, which are rotations of molecules. So they're lower in energy in terms of their separation, but still discrete. And then you have these larger gaps, which are the electronic modes, the UV vis accessible modes. These ones tend to also have signature information, but because there are comparatively fewer of them, you're not getting as detailed of an information set. But that kind of electronic gap is very useful when you're talking about the semiconductor industry and things like this, where tuning that gap between the energy states is very important for the designer properties that you want out of your material. We're going to be focusing on the vibrational states here today, but all I want to say is that even though these things are quantized, different materials have different quanta for where these things lie out. Which is to say that by looking at the spacing of these bands and by probing these using electromagnetic waves, in particular in the mid-infrared, you can get a fingerprint as to what that material is. And so you can learn about how it exists, but also how it relates to other molecules nearby it. So this is really valuable. And so the way we do that in the infrared is we probe the vibrational modes of a material. So I have an example here. So you can think of this as carbon bonded to hydrogen here, but a similar structure is seen in oxygen bonded to hydrogen, so water. And you have different accessible modes which have different allowed energy level. And here they're represented by what wave number they're excited by. So we have the idea of a symmetric stretch. So if we look over here, my arm's going in and out simultaneously. We're moving symmetrically. We can also have an asymmetric stretch, which has a different energy level. But then you can also have other bending deformations. So you can have a rocking motion or a scissoring motion. All of these are different allowed energy states, which have different particular signatures for the carbon hydrogen species. So here they're listed in wave numbers, and we're going to be talking a lot in wave numbers. Wave numbers might be a unit of measure that you're less familiar with. And so for the example here, I have two wonderful Nobel laureates, Einstein and Raman. Einstein, photoelectric effect. He likes doing wavelength in meters, frequency in hertz. These are maybe the more common measurements of light that we've seen. Sorry, I'm not interested in Einstein today. We're going to be looking to Raman, who prefers inverse centimeters or wave numbers. So when you think of 1/cm, that is what a wave number is. Thank you, Raman. So some of you, again, might have some experience with wavelengths and frequencies. So some intuition I have here based on the chart we have. If I'm talking about 2,926 wave numbers, so this asymmetric stretching of the CH, that's equivalent to about 3.5 microns, or 88 times 10 to the 12 hertz, or 88 terahertz. Then there's 720 wave numbers, so that's a much lower energy. That has a much longer wavelength, so that's about 14 microns, or about 21 terahertz. So this is kind of the range that we're going to be working with today, typically on the order of 15 microns to about 2 microns. This is always a battle in the scientific community where different people use different units to describe the exact same thing. And even practically, when you read papers, if you go to lower and lower energy for like lower than 700 wave numbers or 500 wave numbers, people will start talking in terahertz. And they'll start talking in, tens of terahertz or ones of terahertz. I think the fundamental thing goes to these disparate communities, which all had their different unit of measure that they preferred to use. And then as people start to intermingle a little bit more, you start to see some of these clashes. But anyway, I just want you to be aware that we're talking in the range of 2 to 20 microns. Now, FTIR, or Fourier transform infrared, has been a very well adopted technique in science and engineering. It's been around for more than 50 years. This is just the case of Bruker's first FTIR spectrometer, which was a vacuum spectrometer released in 1974. So you can see it's very, very large and very well integrated. But the big things here are that you have been using these infrared spectral signatures for decades now in order to learn more about materials. On a kind of micro scale, not yet at the nanoscale, kind of one of the newer products from Bruker was this FTIR microscope, the Lumos 2, which then has micron level lateral resolution. And so this is a case where we're looking at a film, a polymer film that you're just looking at the cross section of. So this is like a cling film material, and it has these different layers of the cling film. And then you can see what that different layer is chemically. What is polyethylene? What is polypropylene? How do you bind them together as an example? There is an issue though. As you try to study smaller and smaller materials, you start to get into this challenging notion of the diffraction limit. And the diffraction limit defines, based on the wavelength of light, what is the smallest material that you can distinguish from adjacent materials to it. So here is an example from the CDC of an E. coli. And you can see that it's about 500 nanometers times 2 long, 1 micron long. And if we think that we're talking about on the order of 2 to 20 microns, the diffraction limit is 1/2 of the wavelength to a first approximation. So if you try and look at this using a traditional IR microscope, you don't see a lot. So this is to scale. This is a 5 micron spot compared to this little E. coli. If you're looking at just one E. coli, this isn't a problem because you kind of can still sense it underneath that area. But if you have 2 E. coli next to each other and they're maybe slightly different from each other, you can no longer distinguish those from each other. So we need to go to smaller and smaller length scales in order to determine what these things are. I want to start to talk about some Santa Barbara innovation, and that is with Virgil Elings. So if you don't know Virgil Elings and his work in atomic force microscopy, maybe you know Elings Park or Elings Hall at UCSB, which are his namesakes. But he went off to form Digital Instruments and develop the first commercial AFMs decades and decades ago now. If you haven't ever seen an AFM, some of the really impressive things about it are that you can get these really nanoscale level maps of materials. So this has been true since the invention of AFM. So here's an example from 1992 from my alma mater, University of Toronto, where they're looking at the resolution of a calcite lattice. But then also this has been innovated and continued to develop, where now this is being used to look at 2D materials like graphene and how to engineer the electronic properties of graphene to become a next generation semiconductor material. But here we can see not only this kind of hexagonal pattern, which is corresponding to 2 layers of graphene stacked on top of each other and just twisted slightly so that you have this kind of beat pattern that looks like these hexagons, but you can see the individual atomic lattice down here in these little wiggles. So you get this really, really deep, detailed information. How that works, I'm not going to go too in depth here, but just to see how an AFM is kind of positioned, you have this microscale cantilever that comes down to an atomically sharp point. And you kind of drag that across the surface or raster it across the surface, and you measure how much that cantilever is bending based on what is happening on the surface. And we measure that bending by bouncing a laser off of the back of the cantilever and then sending it to a photodetector. And this photodetector, as the cantilever bends, you'll see the wiggles on the photodetector, and then you can read those out and turn that back into how much the cantilever is bending effectively. So I'm not going to go too much deeper into this other than to say that this is really kind of incredible that this works in the first place and that we are able to measure these nanoscale level features using it. But at this point, there's no chemical selectivity here, right? We've not introduced spectroscopy to what we can do here. And that's where this man comes in, Professor Alexandre Dazy from the University of Paris-Saclay. So he's won a number of awards now as a part of his development of this technology. He looks quite stern in this picture, but I want to let you know that he's also a very effective foosball player.
And he makes a mean crate.
He's also a very, very talented cook, yes. But to break these things down, Alex kind of had this idea of, we take the AFM, we take infrared, what do we get? And so this quote from him was, let's buy an AFM, let's combine it with a laser and detect the expansion. And that is the birth of this idea of what is now called AFM-IR, or atomic force microscopy infrared spectroscopy. So obviously we're not going to go way into the weeds of how this works, but a simple mechanism is up here. What we do is we shine a laser onto the tip sample area, so that atomically sharp point for the AFM where it's scanning over the surface. And we use an infrared laser and we're illuminating the surface with that. And so if the sample absorbs that wavelength of infrared light that you're shining on the surface. So let's say we're using that 2926 infrared light again. You're going to take in that energy in the molecules and they're going to heat up because they've taken in energy. And that heat up is going to cause them to expand and move outward. And this expansion is really, really small. It's on the order of an angstrom, so like less than a nanometer, on the order of a single bond length between like a carbon and a hydrogen. Really, really small. But because we have such a sensitive force detector on the tip sample area, we measure that force being applied to the cantilever, and we can read that out. And it turns out that the amount of energy that the sample takes in is directly proportional to how big it gets when it feels one of these pulses, which is what you measure with FTIR for 50 years now. So just like this, you're able to measure an FTIR spectrum, this very useful technique for sensing chemical information, but you're only measuring it where your AFM probe is interacting with your surface, which is on the order of a few nanometers across. So we're getting this very, very highly focused image. And the video here now, the bitrate is maybe not the best of what that looks like, but effectively, we optically define an area of interest, and we use our AFM to scan over that material to find what we're actually looking for. So here's our image, and we identify, I want to look at this spot. We're going to put the probe on that particular location, and we're going to start to shine our infrared light on it. And that's going to cause this probe to start to wobble. So because we have that laser that detects the position of the AFM cantilever, I guess we'll first look at what's happening when things are heating up. You can see that they're expanding outward and they're pushing back on this AFM cantilever. And now, using the AFM itself, we're just detecting the wobble. And so by measuring it, that magnitude of that wobble, you end up getting the infrared response in this material. So we're now taking that in, and then we'll look at the spectra. So you're going to change the wavelength of the light that you're using, and you're going to measure the wobble at every single wavelength. And through that, you get a measurement of the local absorption spectrum just beneath that AFM probe. And so now we can look at these different areas on the sample, and you can see how they all have distinct chemical natures, far beneath what you would see with infrared spectroscopy alone. So this is very, very impressive, and the ability to do this was quite revolutionary. But that is only the start of the story of how it works in the first place. But to get where we are today, it takes a lot of innovation, both on the research side, but also on the engineering side. So I have condensed timeline of AFM-IR development up here. But what I want to say is really the innovation starts in 2005 with the discovery of this technique by Alex to where we are in 2024, 19 years later. So a lot of things happened along the way from when that started to me being in here talking to you all. And so let's first take a look at that 2005 paper, ironically enough, on a bacteria. So we're looking at this individual bacteria on the surface again. It is about a few microns long in this case. And you can put your probe on the spot, and then you can measure that infrared spectrum. And so this black dotted line up here, or the black more solid line up here, is the measurement that Alex took using this innovative technique. And then this dotted line beneath is what they measured through FTIR. So again, you're seeing this direct relationship between the magnitude that you're measuring through AFM-IR in FTIR in 2005, 19 years ago. And then you might think, wow, that's such an incredible thing. Why didn't he start selling it immediately? He could have made a lot of money. And the reason is the laser that he used to measure this is what is called a free electron laser. The kind of more miniaturized lasers that we'll be talking about in upcoming slides were not invented at this point in time. So this is not even half of what the free electron laser looks like in Paris. It's about 25 meters long, and it has a particle accelerator that then goes to this area here where all these magnets are that makes the electrons start to wiggle and release light as a part of that wiggling. So this is a massive, it's a complicated instrument. It's very fraught. You can't exactly sell this to everybody. So I have one millennial base joke over here. Drake is not interested in the free electron laser. Drake wants something which is much more miniature, much more portable. That's my only millennial joke. But that brings us to the first generation nano-IR system, which came out 5 years later. We use this now miniaturized technology called an OPO, or an optical paramagnetic oscillator. And so now we're getting from something which is room sized or larger to something which is a benchtop size. And this is all thanks to, well, a large community of work, but I want to call out 3 specific people who are Kevin Kohler, Craig Prater, and Roshan Shetty. So these 3 people were a company called Anisys Instruments, and Roshan in particular was very influential in licensing the technology from Alex. And then Kevin and Craig were instrumental in developing out the technology and the applications around it. Now, I can't do this story justice. You know, I wasn't exactly here at the time, but I know there are people in this room like Yvonne who are very much involved in maybe hearing what is going on. But it really is an amazing story of taking this thing, which is room sized, and then bringing it into this much smaller, truly sellable type of system, which means that people can start to innovate on it and start to look at different ways to optimize it. And so the thing about a first generation technology is the clock doesn't stop there, right? When you come out with this technology, you don't say, here this is to the world, we're not going to change it ever again. Because once you've made something which is accessible, people will start to tinker with it. They'll start to try different things with it. And they might be able to do something you weren't able to do before. So the first example I'll give here is the way the light goes from the laser to the sample here is it goes underneath the sample and it goes through a prism and then touches the sample where you then measure this out. So practically this makes a lot of sense. This is kind of similar to what you do in FTIR in the first place. But in terms of having a large variety of samples available, it means you're restricted to thin, transparent samples that you can place onto a prism. And so that restricts the type of applications you can do with it. It's also, at this point, only sensitive to materials which are upwards of 50 nanometers thick, which seems pretty thin, I think, in most contexts, but in the context of nanoscience, is really immense. And so you're looking at materials that have to be smaller than 1 micron, but larger than 50 nanometers. You're really restricted in the type of material that you can use to look at it. And so in 2013, other researchers started looking at this, and they figured out ways that if you resonantly excite the cantilever, instead of just using a single pulse at a time and measuring it out, if you actually use the cantilever as an amplifier, you're able to measure much, much thinner materials. And so here, this is just a proof of concept of a polyethylene glycol material. So there's 2 carbons bonded to oxygen, bonded to 2 carbons, repeated over and over and over again. And they made a monolayer of this material where you can see the difference between not being on the material and being on the material is only 2 nanometers. And as they take the spectra over this, you see that when you're on the material, you get your signal. When you're off of it, you see nothing. And then when you're on it, you see a signal again. So down to 2 nanometers by 2013 versus the 50 nanometers that you were seeing in 2010. It really is a massive improvement in the types of materials that you can detect. At this point too, they kind of redid the entire way the system is excited. And rather than going beneath through a prism, they used a focusing mirror to go in from the very top of the sample, which means you're no longer restricted in terms of how thick the sample can be. So not only can we measure down to 2 nanometers now, but we can look at thicker and thicker materials and measure their nanoscale properties. So you really open up the application space there. We're going to jump ahead now to 2018, where there's a little bit of a schism, where the AFM portion of the technology, the AFM-IR that I'm going to be talking about for the rest of the presentation today, is acquired by Bruker. And during this time, and particularly into the later years of ANSYS, they started to work on this new technology called optical photothermal induced resonance, or OPTIR. And they felt that that had enough legs to go on its own, and they've started to develop it further. And it's become very, very successful for them. And so, I mean, Craig is, again, in Portugal right now, talking about this technology. So they're still in Santa Barbara, we're still in Santa Barbara, but we're just looking at slightly different ways of exciting our samples. And then that brings us to where we are today. We've released a few additional platforms since then, but we've really looked at how we can push the technology further and further. So one of the examples I have here is another fundamental study where we're looking at an even thinner material and even shorter length scales. So this is an example of a small molecule. You can see it's about 5 nanometers long in total. Cast them out onto a surface such that they self-assemble into a herringbone. So they kind of stack over each other. But it's still a single layer of these materials. They're just lined up side by side, like in the first class seats on an airplane. And what you see when you have this is a material which is less than a nanometer thick, so about half a nanometer to 0.8 nanometers thick, that you can measure the spectrum on. So that's this blue curve over here. And when you map out at this wavelength, that's what this looks like, where the green is areas of intense signal and the purple is areas of lower signal. And you see this beating pattern, which corresponds to the length of the molecule itself. So you're seeing this self-assembled structure less than 10 nanometers on the order of 5 nanometers across. And if you look at the signal variation, you're really detecting variation on the order of 1 or 2 nanometers. So that's really an impressively small size scale to be able to look at. And this is only based on the kind of iterating and development process that comes into, you come out with a new technology, the community grabs a hold of it, they see how it could be made better, how small improvements that could be made, and then re-looking at those technologies from an engineering perspective and making the instrument better as a result. So this has become a very fast-growing technology. It grows considerably year over year. Here is the Google Scholar results for AFM-IR year to year. But I really want to strongly emphasize this fact that we've already been talking about, which is that the scientific advancements of today are based on the previous knowledge. And so if we can kind of break out what the kind of innovation breakdown looks like here, you see this first section of papers that come out every year, which are really about these fundamental questions. So how can I take a very simple sample? How can I put it onto a material and learn something about how the instrument works? But those ideas of learning how the instrument works, which are kind of the first step to a technology being adopted, then start to help answer simple problems. Now, simple doesn't mean easy in this case. It simply means that there is a relatively direct way to measure them, which is the case here. So we're looking at another cling film material. That this is literally like a store-bought cling film where you can take a section of it and you're looking at the cross section of that thin film. So you're looking at a very, very small area. You can see it's 25 microns across, but it's really made of different layers which have different properties that the manufacturer is interested in building out. And so with this, we're able to reverse engineer what this material is made of by looking at that infrared fingerprint. So we can see some areas are made of polyethylene, this A area, just by looking at the spectrum here. We can see the C and E, which are polyamide, which affect the air permeability of the material. And then you have these other layers like D, which is an ethyl vinyl alcohol, which is a tie layer, which allows the material to be compatible with itself. So you're able to break out all these things, but this is still very fundamentally a simple problem. These things are very well segregated. You can see where the individual layers are visually using the AFM before you decide to take your spectrum. But then you get into, based on this knowledge, based on what we're seeing here, which is that relationship between FTIR and AFM-IR, you start to do these applied research problems. And so these get into the much more complicated analysis. How can we learn much more about the material itself? So this is a post-consumer recycled plastic. This is a material where they have taken it, you know, your PET bottle, they've broken it down, they've remade it, and then they've want to characterize it. And when you look at the topography, you don't see anything, right? It looks basically homogeneous. But when you start to look at the infrared intensity, you can see variations in two kind of unique domains here. But it goes a little bit further, and this is where we're getting into these questions of applied research of how can we learn really much more about the sample itself. And they start to do kind of advanced computational analysis of this. And you see that not only are there two domains, but there are actually three domains. So there is one area, which is primarily polypropylene. You have one area, which is primarily polyethylene. And then you have this considerable crossover layer between polypropylene and polyethylene. This is important in this context because the mechanical properties of the post-consumer material is based on the chemical properties. And the fact that polyethylene and polypropylene are largely immiscible with each other weakens the plastic overall, which means that you're able to recycle it fewer and fewer times, and you get work in each of those times that you recycle it. It's a good chance to go on a break. So, kind of the fundamental backbone that we're taking into the second half of this presentation, but it's really the fact that we're building on existing research and existing technology to answer larger and larger questions. And so the next two sections of my presentation are about how AFM-IR is being used to answer big questions in the cosmos and how we can become healthier because of it. So first, I want to talk about the cosmos. So we're going to be talking a lot about the sample return mission in a moment, but this is an image or an artist's rendition of the Hayabusa 2 return mission, wherein the JSA, the Japanese Space Agency, sent a satellite to an asteroid to collect samples from that asteroid and deliver them back to Earth. This work is done by Jeremy Matsuon, who is also an avid foosball player. And so a lot of the slides in here are with his thanks and with all of his help. So the first thing I want to talk about is micrometeors. These are the most studied extraterrestrial material on Earth. Why? Because we can get them. And so the easiest way, or the most reliable way people have collected pristine micrometeorites, is by going to Antarctica. And so you have this fall off from space from space debris, and you look in the Antarctic ice, which has been frozen there for thousands and thousands of years. You dig out these large quantities of ice and you put them into a bucket. And then you put that into a specially designed melting room where you can then separate out the ice from the material that is existing in the ice and then collect that off and filter it. And so you get materials that look like this, which are just a few microns across, but have a lot of different variability in them. And they're really a good, effective way to study what is going on in the early universe. And so these things are studied in a number of different things. But here is an example of looking at one of these samples from Antarctica called a UCAM, or an ultra carbonaceous Antarctic micrometeorite. So quite a bit of a mouthful to say, but the key things here are that it's the big first step is that it's ultra carbonaceous. That is to say, it has a lot of carbon containing materials in it. These are suspected to be where the material that life exists on in the world kind of got its start. So where particles from space came onto Earth and provide the carbon that is then necessary for life to exist. And so from this, we can see the micrometeorite. Here it is in an SEM, and here in the AFM itself. So you can see that it's actually quite flat. This is an important part of studying these materials, is that you want them to be as homogeneous as possible. There are a few different ways that you can do this. In this case, what they do is they take 2 pieces of diamond, so very, very hard material. They take the micrometeorite and they physically squish it between those 2 pieces of diamond to get it to a defined thickness. But the defined thickness is very important because AFM is so sensitive, you want your material to be as flat as possible. And so when we look at this and we take spectra over it, you start to see these kind of variations in the spectra from location to location. And we can map that out. And so you can see, in particular, we're going to look at this area from 1,000 to 1,500 wave numbers. At 1,600 wave numbers, it corresponds to the C double bond C interaction. What this corresponds to in extraterrestrial materials is polyaromatic hydrocarbons, or PAHs. You might have heard that term before because that's also the concerning material that comes in the soot that comes out of cars, right? So you have these highly cross-linked pieces of carbon networks. And so you are already starting to see that you have these, this ultra carbonaceous, you see these large areas of these PAHs in this orange map here. And then you can also see this carbon bonded to oxygen functionality. This corresponds to carbonate materials. So you can think of that as the kind of carbon-rich rocks that exist on Earth as well. And so we're seeing that we can map out these carbonates at 1710 wave numbers, and the C double bond C from the polyaromatic hydrocarbons at 1600. But what Jeremy was also able to prove to these researchers is that he could detect when materials were contaminated. And so what you see here is the separate area where you have these blue functionalities. And these he identifies as spurious materials. The reason is, if you look at the spectrum, materials from Earth look very, very different from materials from space, where materials from space have been bombarded by cosmic rays for years and years and years, to the point where the spectra kind of smear out. Whereas if something is very, very sharp, like we expect from like these highly quantized materials, almost assuredly they're coming from Earth. And so he's able to see that he has these sharp functionalities in the surface as well, which correspond to these spurious materials. And this got the other researchers really, really excited and wanting to explore how AFM-IR can be used more to look at these samples. So here's another bigger picture of looking at that relationship between the carbonates and the PAHs. Okay, so then in a similar material. This is another ultra carbonaceous material. And they want to look at the spatial resolution of the technique. And so here they find this material. We're also, again, looking at these carbonates and at 1500 for the PAHs. And you can see that in this line across here, the variation in the three signals. So 1020 corresponds to the background. So what is the actual material that it's being transported in, which is a silicate meteorite. And then you see that you have these areas where the silicate is high and also the carbonate is high. You see areas where the silicate is lower and that you have more of these PAH materials. So you're really seeing the sequestration of the smaller domains within the meteorite. And so this is giving you information on how these meteors are formed and how they're all compressed together. The really impressive thing for the researchers, again, was looking at the relationship between the AFM-IR result and what they get through FTIR, which is FTIR, you're measuring this whole material now. But so what you're seeing looks like an average of the entire material. Whereas we can now go and we can see the areas where, okay, carbonate is higher, where PAHs are higher. And if you kind of ensemble all of those and take an average of all of them, they look like the FTIR spectrum. So you're getting the secondary confirmation of what you're seeing on the nanoscale with the macro scale. And so in particular now we can look at just the organics, so broken up from the substrate, where you see areas where the red is higher, you're seeing more of those carbonates. And when you're seeing the areas that are more green, you see the PAHs. And you see that almost always the PAHs are associated with a higher carbonate content based on it being yellow over here. But in general, the carbonates don't need to be associated with the PAHs. So that gives you information on how they're sequestering. So that's really exciting, but it's fundamentally limited, which is that when you're looking at a meteorite, you're looking at what has come from the parent body in a much more reduced capacity. So it's gone through Earth's atmosphere as it's landed on Earth. A lot of it has burnt up in the upper atmosphere. And by the time it gets to us, one, it has been exposed to lots and lots of heat, so the structure could physically change. But also, you're only seeing what is at the very center of that material. And so what we want to be able to do is look at the exterior of that material. And this is where this Hayabusa 2 mission really comes in key. So previously, people have studied asteroids, infrared in particular is studied and used a lot for astrochemistry. The James Webb Space Telescope has an infrared detector for these kind of purposes. But we really want to have something back on Earth so that we can measure it with a very high lateral resolution and really figure out what's going on there. So the story of the Hayabusa 2 mission, again, it was launched in 2014. 2018, it arrived at the asteroid and it began to do significant remote sensing of the material. So it has a number of detectors on it already to determine what type of material the Ryugu asteroid is made of, information like that. And then after that, it landed on the meteor. It took a sample of the material, or it landed on the asteroid, sorry. It withdrew, and then it sent a small impactor device to make an artificial crater in it. So not only are you measuring what is at the very surface of the material, but you're measuring some subsurface material that you wouldn't have been able to measure otherwise. And so it comes down again and it takes in that material as well. And then it departed in 2019 and returned to Earth in 2020, where we now have these samples. These samples are extremely precious. They're some of the most expensive materials on Earth. When researchers hand them to each other, they have to hand carry them from one location to another. And this is very challenging if you look at the dates that are associated with this mission, because this happened over the course of COVID, in particular when Japan was under a full lockdown. So they had to get special dispensations in order to transport these materials to each of the researchers. But when we look at that, we see something that's really, really impressive. So these materials are based in kind of two different categories. One are the crater materials and one are the surface materials. So this one, it has a defined code associated with it that you know is from the crater in particular. And what they did is they sectioned these really thin. In this case, they're using a diamond knife to cut through them and cut them at a defined thickness, which for a meteorite or an asteroid is extremely hard to do because there can be very fragile in some locations. You can have very hard areas and very soft areas such that it can be hard to cut through. Like imagine when you're cutting through like a bagel with raisins in it. You know, you very rarely actually cut through a raisin. You more likely kind of bend around that raisin and get it on one side or the other. So you really want to cut it in such a way that you're capturing all that material throughout it. And so when they cut these very thin, they then send them to researchers around the world to characterize. And so in particular, this one went to a synchrotron first, where they looked at the infrared map of the functionalities. And what they see in this material are similar to what we're going to look at, which is, so you see the larger matrix in green, but then you start to see the PAHs located in one location, and then the carbonates in another location. And then we're going to drill down on the areas that are particularly bright here. So we're going to use the faster, larger scan to then direct the AFM-IR analysis to really dig down deep in. So when you do that here, what you see is the distribution of the network of the material, but then you start to see these pockets of organic matter, right? And so these are more protected than just kind of being distributed everywhere in the material, which kind of gives us a sense of what is happening when these asteroids would have arrived on Earth millions of years ago, and how kind of the organic materials in the universe might have found their way onto Earth. There you go. But also, similar to that ZAG meteorite sample, in the Ryugu surface sample, so this is the A sample, which don't come from the crater, what you see is a similar story of organic material within the sample. And what you see is in some areas, again, you have more of these carbonates, in some areas you have more of these PAHs, but you also have carbon-hydrogen bonds that are starting to be revealed. And they're not necessarily related with each other. So if we look at the spectra corresponding to S1, S2, and S3, you can see that in areas where PAHs are high, the CHs are also high, but the areas of carbonate don't necessarily go along one-to-one with those. So you're starting to get information on how the organic material is sequestered within the sample and how it's distributed. So this is really, really exciting stuff. And we're able to see a lot about the origin of the building blocks of life within these meteors and asteroids. But the researchers, and Jeremy in particular, doesn't want to stop there. So the next steps in terms of this research are getting a system with a large environmental control around it. So this is an example of an AFM in a glove box. They want to put an IR system in this glove box such that you can always keep it without Earth's atmosphere being exposed to these samples. They're super, super precious, and it's hard to sometimes see what happens when you take one out of a vacuum environment or out of a not sensitive environment, and you expose them to all of the oxygen in the air, which can cause them to oxidize and change. And there's all of the carbon in the air as well from us breathing in and out that you try your best to be careful about, but you ultimately can't avoid. And so they want to have this well-defined sample chamber that they're going to then test their samples through again, because they're ultimately generating justification for the Mars sample return mission from NASA in 2030. So they're going to take the Mars samples under a similar study as the Ryugu samples and really look at the nanoscale and try and see, is there organic material on Mars that has to this point been undetected? It's not as kind of vast as saying, can I detect a bacterium on Mars or something like that? It's just, do the building blocks that exist on Earth, are those also present on Mars? So that is all very interesting, but it's a very large scale cosmological study. And for the rest of my presentation, I want to look at 3 short stories of how AFM-IR is being used to help us be healthier. And there are a lot of people to thank in this case. I can't put them all on the slide, but I will especially shout out one of my colleagues, Jinhee Kim, who's an application scientist at Bruker now, but some of her PhD work is included in the next few slides. So the first thing I want to talk about is looking at drug encapsulation. I'm not going to spend too long to talk about this, but this paper came out in 2019, and it became a much hotter topic after 2019 because drug encapsulation and drug delivery is the #1 way we design mRNA vaccines in the modern day. And so this example is not quite the same as the mRNA vaccine, but it's very analogous, wherein we have what is a lipid vesicle rather than a lipid nanoparticle. The major difference between these two things is just the size of the particle effectively, and so how much drug is loaded within it. And so when we look at this liposome, we can put a molecule in it. In this case, this is cytarabine, which is a chemotherapy drug that they want to engineer to be better targeted within cells. So you'll have fewer healthy cells taking it in and feeling the ill effects of chemotherapy and more targeted towards the cancer cells itself. The problem statement being there's not really effective methods to measure if a particle actually has drug loaded in it. So typically what kind of companies do is they work on a bulk reactor scale, right? So they'll have a mixture of compounds that come together that then do this encapsulation and drug loading all in one. You want to do it in as few steps as possible because that's how you engineer the economics of scale into this. And so typically how they verify these materials is they will take them to a liquid chromatograph or a standard FTIR measurement like that, which will tell you, yes, I have liposome and yes, I have cytarabine, but it won't tell you my cytarabine is in my liposome. So people have evaluated this using fluorescent tags. And so you can put a molecule attached to the cytarabine that fluoresces, and then you can look at the particle and see if the particle is lighting up or not. The challenge with that is these fluorescent tags can often be very, very big. So on the order of tens of nanometers. And if you're talking about a vesicle, which is on the order of 80 nanometers or smaller, you're starting to encounter size restrictions in terms of what you can load into there. And so with AFM-IR, they're able to look at these particles and look at the map for, in this case, the cytarabine signal at 1528 wave numbers. And so you can easily tell a liposome which is loaded with the molecule. One, it's become more rigid, but 2, you can see these spectral signatures within the particle compared to one that doesn't have it, where you can see it's much more oblong because there's nothing within the lipid vesicle, but also you see no signal when you're looking for the cytarabine signal. So this is really helping you understand what is happening in terms of these drug loading things. And regulatory bodies are starting to look at this technology as ways to verify that the drug is actually loading within the vesicle or within the LNP as part of a drug delivery and drug certification scheme. So that's really what I have to say about drug encapsulation. But the other thing is understanding how diseases develop in the first place and how we can design drugs to manage those diseases. And so now I'm going to be talking about amyloid beta. Amyloid fibrils are a strong suspect in the neurodegeneration pathways of Alzheimer's disease. And so what happens with these is you have these protein groups on their own that then begin to misfold. So they, I'll talk about this in a brief second, but they form a conformation that they're not supposed to form into. This is how other prion type diseases like mad cow disease also form. And then from here, they kind of start to aggregate together. And when they aggregate together, they form these longer and longer fibrils, which again are associated with neurodegeneration. When we look at brain sections of people who have passed due to Alzheimer's disease, you will always see these large amyloid fibrils corresponding to where you see areas of neurodegeneration. So I briefly want to talk about protein structure. This is a very complicated map, but just to say that the proteins that your body makes fold into specific shapes based on their chemical structure. And these structures have these higher ordered names that we use to refer to them. So we can see these spirals that we call alpha helices. You can see these green ones, which you call beta strands or beta turns. And then there are also loops and turns that are called random coil. And so the reason proteins form into this way is because you can generate certain activity sites for the protein such that it can do its job in a better way. And so you'll have the kind of bound molecules, which will either be something that the protein is acting on if it's an enzyme or some signaling pathway for the protein. And they have these kind of lock and key structure where these things can fit together. So how can we study this? The interesting thing about these beta sheets, alpha helices, beta turns, is that they have a different chemical signature, a different chemical fingerprint associated with them. So when you look at them and you look at, in this case, a bunch of blobs of amyloid protein, you can take a spectrum on them and you can say, what fraction of this material is beta turn? What fraction is alpha helix? Which you know what the ratio should be for the properly folded protein. So this is going to tell you if my protein is misfolded or not, and also how it's misfolding. So after you incubate this for some time, you can see that it starts to form into this strand-like structure. And so these are these amyloid beta fibrils, which are associated with neurodegeneration. And then we can take spectra over them and see what's happening. And so when you take the spectra, you can look at the average misfolded oligomer. And we're going to look at this one over here, which is maybe a little bit of an eye chart for some of you in here. But the big things are that in the native oligomer, you have very little beta sheet content. But as you go towards the misfolded oligomers, that beta sheet content increases. And as you go to the amyloid fibrils themselves, the beta sheet content increases even more. So this is giving you a not necessarily a smoking gun, but it's starting to give you hints at what is happening as these proteins misfold. You're forming more of these beta sheet structures. So what if we can disrupt the formation of the beta sheets themselves? And so there have been a few researchers who have experimented with different methods of doing this. The FDA has also approved a targeted drug, which is supposed to disrupt the formation of beta sheets within amyloid beta through a protein. But this is a small molecule example of bexarotene, which is actually FDA approved for treating certain types of cancers. But the big thing here is that it's got these groups over here, the oxygen groups, which are known to disrupt the hydrogen bonding formation and the structure of these beta sheets. And so when we look at that practically, what you can see is the bexarotene, it's got this spectrum here. But when we look at fibrils versus fibrils incubated with the bexarotene, you start to see this larger peak at 1730 wave numbers. This is notable because that's not present in the bexarotene, right? So that's not something that is just a signal due to the bexarotene itself. This is the actual bexarotene monomer, which is disrupting the formation and the aggregation of the amyloid beta here. So this is giving some hints as to how we can potentially slow the Alzheimer's development process, or even in a larger scale, reverse it much further down the road. Okay, and so my last example here comes down to physical fitness. And so I'll kind of just say it in the title, the repetition is an essential component in movement, right? You're not just doing one action and then you're stopping and that's it forever, right? So even down to taking a walk on the beach or doing sports, you are repeatedly using your joints and straining them out and then relaxing them, moving them over and over and over again. Now, this is generally not an issue, right? Your body is designed to do this, and you have healing pathways for your ligaments such that they're repairing at a rate which is faster than the rate that they're being damaged at. But as you start to look into more high impact sports, you start to see issues with this. And you can begin to see failures, especially in people's ACLs, that correspond to repeated use. So you can have these kind of instantaneous contact failures where somebody is like hit in the knee or kind of falls in a weird way such that their ligament is stretched beyond the breaking point. But in general, most ACL failures happen over continuous usage of your ligaments. And so if you've seen the movie Challengers, this happens to Zendaya, where she is playing tennis one day and she turns in a weird way and her ACL just fails. And that's a career-ending injury for most athletes. So we want to be able to study this, but then we need a controlled way to be able to wear a ligament versus looking at a regular ligament. So I have a content warning before this because I'm about to show a gnarly little clip for about one slide. Especially given that everybody's just had their lunch. I think this is an important thing to have here, that what the researchers have done is they have taken a knee joint and put it in a device to repeatedly stress it. I find this hard to look at sometimes. So, yeah, it's gruesome. But effectively what they did is they used cadaver tissue and they look at an internal control knee, right? A knee from the same cadaver, which should have had similar conditions to that cadaver. And then one which is going to be tested. They put it into this mechanical device and they simulate loaded jumps. So just somebody jumping over and over again with 3 to 4 times their body weight for 100 cycles. All things considered, this is not a critical injury, right? So you can do this jump right now. Your ACL should not fail, and even over 100 repetitions, the ACLs in the study don't fail. But what it does is it puts this wear and fatigue onto the ACL, which is faster than the rate that the repair cycle should happen over. And we have the internal control to compare to. So we take these really thin sections of these again, and you can look at the protein secondary structure again for the ACL. So similar to amyloid beta, actually, your ACL is based on woven protein fibers that form into these larger structures. And when we look at it, we see that in the controlled cadaver, the main peak corresponding to that protein is at 1660. But as you test it, you can see that protein, the collagen, shifts to 1740 weight numbers. So you have a change in the chemical structure due to this wear cycle and an unraveling of the collagen fibers. And so if you look at a patient ACL from somebody whose ACL has failed, you see a similar result where you see this highly disordered collagen. We can also look at this using fluorescent markers, where you can attach a fluorescent marker that targets specifically the unwoven collagen, and you see a similar result, right? So we see these areas where you don't have any variation in the control example, or in the tested example where you start to see these areas where the protein has unraveled, right? This is this mechanical wear that you're putting onto your ACL. And so when they study this in a more deep way, what they start to see is that when you use the spectroscopy and you look at the relationship between the unraveled and intact groups and the mineral content, so how much mineralization is in the tissue, areas of higher mineralization correspond to higher unraveling. And so you're starting to get, again, this hint of what is happening in terms of how the proteins are starting to wear and unravel. And we are seeing this linkage between mineralization and tissue mineralization and what is happening in terms of the unraveling and ultimate failure of ACLs. So that's a very, very brief umbrella overview. I wish I had more time to talk about all of these things, but I'll just end with my conclusion to say that we're looking at this kind of more meaningful measurement based on all of the information that we've learned through developing the technique and these fundamental questions that we can then use to answer these bigger picture questions: how we can be healthier, how we can reduce neurodegeneration, what is the origin of the building blocks of life in the universe. I think these are all really impactful things, and AFM-IR has a significant role to play in all of them. It's not the be all and end all. It's not like every single researcher from today onward needs to use an AFM-IR, but it does provide a critical piece of the puzzle in understanding this further. And all of this work is kind of built on the backs of giants, in particular Craig, Kevin, and Roshan, but also Alex and his team at the University of Paris-Saclay, and the AFM-IR applications and R&D team within Berger. Okay, went way over time from when I thought I would take, but I'm happy to take any questions.
Questions from the room or from the Zoom? You can raise your hand in the Zoom.
The AFM-IR probe, I'll just use a general term, its use on a system.
Yeah.
The introduction of that is going to cause a disturbance by the presence of the probe. Has that historically, and is it a problem, or it's so minimal that it's inconsequential?
It's a very good question, and it really gets to the heart of what you're doing with AFM and the types of forces that are associated with AFM. So ultimately, you will have to disturb the sample somewhat in that you have to have a sample which is relatively thin, and that is on the same size scale that you want to look at with your AFM probe. So that is one problem. The forces, there are different ways of imaging samples using AFM, but fundamentally the forces are very, very low, on the order of nanonewtons or piconewtons. So you're really trying to be as minimally invasive to the sample as possible. The reality of it is that AFMs are used to study live cells all the time. So if you're kind of invasive minimally enough to not disturb a live cell, that's a good thing. That said, you are still fundamentally disturbing it in some way because you have it fixed on a surface or freely attached and detachable from the surface, but you have a surface that it's interacting with and then a probe on top, right? So that does not necessarily reflect your kind of in vivo character where things are swimming around in your body all the time, not necessarily bound to a surface. Yes and no.
I don't want to hog this, but if it's a problem because it's a disturbance, and that's kind of fundamental to it, especially on this scale. Is it sufficient so that you can ignore it, or is it enough of a problem that you have to do something about it? And then historically, what has been done, what is being done to correct the problem that it represents?
What I would say broadly, in the kind of 10,000 foot view, is assuming what you're interested in is measuring the surface, there's no correction that you need to do, even on this highly local scale. That assumption does not hold for all samples. And so there are some cases where, in particular, having your AFM probe is like a lightning rod for your electric field coming into your sample area. So you're really focusing down that electric field, and sometimes that needs to be considered, but that is the exception rather than the rule.
I had a question. Is the FTIR scan and the AFM-IR, can those be done by the same instrument, or is that two different
There's
instruments?
two different instruments. In theory, you could have them in one instrument, but the real fundamental thing is the detector. In the case of AFM-IR, your AFM probe is also your IR detector. Whereas in a traditional IR system, you'll have a camera or some other detector to detect the energy that's coming into it. So that is to say that they have two different detection mechanisms, not to say that you could not integrate them together, simply that there's not a benefit to integrating them.
What's the like demand, or what's the market size for this sort of thing?
So annually right now, we're trying to think of what I can say publicly.
Yeah,
More than one, fewer than 100 a year.
Okay.
In that kind of, in the kind of tens of systems per year. But it really encapsulates a wide variety of people. Lots of researchers and companies are interested in investigating nanoscale behaviors. So that can be the researchers whose papers we've highlighted today, but it can also be companies like Intel who have small features on their semiconductor devices that they want to evaluate and characterize. Or it can be 3M who is doing polymer processing and wants to see what is happening with their polymers at the nanoscale.
Hate this. I don't mean it for that thing here. Are your annual sales proprietary, or is the information public? And if it's public, what approximate volume of sales have you been doing for the last few years, and do you expect over the next few years?
Yeah, so we're part of a larger publicly traded company. So we don't report the numbers specific to the AFM-IR product specifically, right? We're more represent what the overall business is doing. So we report at the business unit level. So Bruker Nano, which is in the realm of $500 million to $1 billion. I'd have to look it up. I don't know it off the top of my head, but that it comprises many different products. And so we don't report specifically what's happening with each individual product.
Hi, I've got a couple questions. The title of your piece here is AFM-IR. Is it only limited to infrared, or is there possible future developments in, say, UV and other wavelengths?
So that's a really fascinating and fantastic question. And it really kind of gets to the heart of how the technology works. No, there is no limitation specifically to the infrared. The infrared is just where it has found the most kind of purchase and people latching onto it. There have been people who have done AFM-IR, they call it a PTIR at that point, or photothermal induced resonance, to study into the visible and beyond. The limitation you start to get to is the size scale worth coupling with an AFM? When you're talking about the visible, you're talking about wavelengths on the order of 500 nanometers to 100 nanometers. So spot sizes on the order of 200 nanometers. So the kind of size scales of things that you get a lateral resolution advantage of by using an AFM as well, it gets smaller and smaller as you go to shorter and shorter wavelengths. And then you can certainly go to longer wavelengths like microwaves and radio waves, but the chemical information starts to drop off in that direction as well.
And also, you mentioned at the beginning of your presentation, the first machine was built with a free electron laser, and you've since gone to the infrared laser. This laser source has to be variable wavelength. I'm wondering if there are other, if you're somewhat dependent on other types of lasers or other laser developments in terms of what kinds of applications you could encompass with your system.
Yeah, that's absolutely true. So getting into the weeds, you must use a pulsed and tunable infrared light source, or light source in general. Does not necessarily need to be infrared. And so having that pulsed and wavelength selection are the kind of two key criteria. Where something like a free electron laser, you can tune the wavelength that it's emitting. In these OPOs or quantum cascade lasers, you can also tune them. In the visible, there are other options as well, but you kind of get the idea.
You got a question?
Yeah, just a quick one about do you feel like you've reduced the size of this apparatus? Have you hit a plateau, or do you continue to miniaturize it?
So at this point, you actually start to hit the limit of people's sample requirements. So going back to the semiconductor example, because they have a very well-defined requirement, which is a 300 millimeter wafer. I want to look at a 300 millimeter wafer. That fundamentally decides how small the tool has to be able to look at that. It's got to be bigger than the wafer.
Questions from the Zoom? Anyone? Wonderful talk. We have a couple of comments in the chat. Says Mary says this has been an excellent presentation on a complex topic. Thank you very much for breaking it down. So, thank you. Appreciate it. And we'll be happy to see people next month for our talk on recyclable plastics. And thanks for attending our meeting.